Hi, I'm Peter Johnson, a PhD student at Dartmouth College. I'm going to today present my work on crossing guard, defending against novel bus attacks. This is work with my advisors, Sergey Bratis and Sean Smith, also at Dartmouth. The work is funded by TCIPG. Okay, so when you're defending against traditional network attacks, where the nefarious fellow in the cloud is attempting to send over the internet an attack on a power station network, you defend this generally in two ways. Either you put in a firewall, or you physically disconnect the networks with an air gap. That is, so that the data cannot physically flow from the cloud to the network that you wish to protect. And these protect against internet-based attacks. However, there are times when this is not effective. For instance, this is a set of uranium centrifuges at the Natanz facility in Iran. This was recently infected by a virus. The trick was that it was not, this network is air-gapped. It is not connected to the internet at large. Therefore, how did Stuxnet infect the centrifuges with its nefarious payload? Well, it was very simple. It was just a USB stick. What happened was the USB stick was configured to auto-run a particular program. The attacker plugged it into one of the machines that was across the air gap, and that machine then was infected by automatically running the program on the disk, on the stick. Then the virus propagated within the air gap network and infected all the other machines. So this is bad, right? And you could first say that, well, I could easily turn this off. I could easily prevent this attack by turning off auto-run. And that's true, you could. However, there have been attacks demonstrated where that would not be an effective defense. For instance, this vulnerability was found in Windows within the past year and a half, and it allows a physically proximate attacker to execute arbitrary code by connecting a crafted USB device. And if you look at the implications of this, they're pretty severe. Complete confidentiality, complete integrity, complete availability, low access complexity, and no authorization required. This is because whenever you walk up to a computer and plug in a USB device, the computer has to say, what kind of USB device are you? And then it has to set up a certain internal state to correctly deal with the communication it's going to receive and wish to send over the USB. So this is bad. This is sort of the unholy set of badnesses. The only saving grace is the access complexity. Access complexity is low, meaning that you have to have physical access to the machine. So again, this is bad. Fortunately, all hope is not lost. We've developed a system called Crossing Guard that behaves as a USB firewall. And just as a network-like firewall, it is both stateful and connection tracking, and we have an in-kernel software implementation. Now, we could have a hardware implementation, but for our purposes, we've done it in software. I'll show on a later slide the little more detailed architecture. What Crossing Guard does is it examines all traffic that flows between a USB device and the host and back. And it will detect and disconnect an authorized device. That is, with a policy, I could say, do not allow any USB thumb drives to communicate with this computer. And Crossing Guard will prevent that from happening. On the other hand, it will also prevent a USB keyboard from behaving like a thumb drive. So if someone plugs in a USB keyboard that says, hi, I'm a USB keyboard, it cannot then start behaving like a thumb drive and doing the nefarious kinds of things that thumb drives could do. And additionally, this supports further custom security policies in regarding specific types of devices and particular actions to take when rules are matched. All right, so let's see how it works. The conceptual model is we have this nefarious attacker who has this malicious USB device. They plug it into a USB port on the machine. And before that attack can actually get to the operating system core, the kernel, Crossing Guard stops it. And this is why we put it in software, so that it runs actually within the kernel code, but actually in the device driver of the USB port itself. So all of the traffic between these along this line will be examined by Crossing Guard and verified for correctness. Now, in order for testing in development, we have this is our proof of concept model. First off, we have inserted a vulnerability in FreeBSD, our victim operating system. That is so that we don't give the real attackers sort of a leg up. And instead of using a custom crafted USB device, we have we have this little board called the face dancer, which you can see a picture of right here. It's a very small board. It's only about 3 inches long. And what this allows us to do is craft arbitrary traffic to send from one machine, the attacker, to the victim machine. And so we have developed in addition to the crossing guard defense mechanisms, we've developed a system to craft arbitrary USB traffic and send it over the bus, and thereby exercise our protection mechanism to show that it works. And right now, we will in fact show that. First, we've got 2 terminals here. The top terminal is the attacker, and the bottom terminal is going to be the victim. Currently showing in the bottom terminal is the output of the system logs. In the top terminal, we're going to run the software that drives the face dancer to simulate the attachment of a real USB keyboard. And we can see the data that goes back and forth. And in the logs, we see that a keyboard has been connected. If we terminate the keyboard up top, we see the keyboard has been disconnected. Great. That's exactly what we hope to see. Now, if we run the attacker, then this is the attack up here. It sends something slightly different, and we can see that. So this is very simplistic exploit, but it just writes to the system log as the kernel, therefore showing that it has kernel privileges. Now we can exit from the attacker and enable our crossing guard defense mechanism. Backspace T = 1. There you go. Okay, so now the defense mechanism is enabled, and we will run the attacker again and show that the exploit is in fact detected and prevented. We can see down here, exploit attempt detected, rejecting, exploit attempt detected, rejecting. And the reason it happens multiple times is because when the exploit is detected, the function call just fails, and therefore the larger USB machinery just causes a retry because it assumes the device is not behaving properly and therefore allows it to give another chance. But eventually it does give up and says, we failed. All right, so lastly, however, we want to show that crossing guard will not just prevent malicious devices, but it will also allow well-behaved devices. So we're going to go back to running the well-behaved keyboard, and we will see that the same lines as original show up, where we have a successful connection, and on exiting the emulator, we have a successful disconnection. Great. Thank you very much.